My name is Mike DeLacluse. I'm the president of the Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for our customer webinar, Pulsed Firing Furnaces Producing Staggering Results. Today's presenter is Jeff Lamore of Kromschroder. Jeff has more than 15 years of experience with combustion systems, starting out as a design engineer for a custom furnace oven manufacturer in the late 90s. For the past 6 years, he's been with Kromschroder, working with customers to improve combustion efficiencies and safety. Today, Jeff's going to talk about pulse firing and how you can achieve improved efficiency as well as improved product quality. You'll also learn it's much easier than you think to implement pulse fire as a strategy. The phone lines are currently muted. If you have any questions and would like to unmute yourself, all you have to do is hit *6 and you'll be unmuted. At the end, we will unmute everybody, so if you want to save up your question, feel free to ask it at the end. Jeff, go ahead and take it over.
Okay, well, great. I'd like to thank everybody again for taking the time out to join us for this webinar. And as Mike said, this is a webinar on pulse firing. I have done quite a few systems with this, starting back in the late 90s when I was designing furnaces. We manufactured pulse fire furnaces, so gone through that road and all the way through designing for commercial OEMs. So basically, what is pulse firing? Pulse firing is, as you can see, a special type of combustion system that offers significant process and productivity benefits. What is everybody looking for nowadays? Fuel savings and temperature uniformity are the two biggest ones that we see out there in the market. Lower NOx emissions, versatile control scheme, improved turn down, and suitable for heating and cooling cycles. A lot of those, the last three, really come into play in your design and your applications. The fuel savings. Pulse firing operates the burners at their most efficient firing rate, high fire and low fire, or off, depending on how we set up the burner system. So you can fire these burners on ratio all the time, as opposed to modulation, where at 50% of firing rate, you don't know where the burner is. Improved temperature uniformity. That high velocity burner will fire the burner and create convection in the furnace, getting improved heat to load. Lower emissions. The NOx emissions are minimized in high velocity flames. Basically, firing at the high velocity, you're going to create a thermal oxidizer. Control design flexibility. The pulse fire systems use the convection to increase the uniformity in the furnace, and maximum turn down basically depends on how you set up the low fire of your burners. So hold temperature 800 to 2300 degrees F on a hot firing system. Maximize productivity. Pulse firing utilizes the system's burners at their most efficient firing rates. Maximum energy to the furnace load. So heat in, you're putting the direct heat in at the most efficient firing rate. We'll go through some of the basic types of system designs. Fuel only control, excess air. You'll see this sometimes with, this system is used to create maximum mixing within the furnace. But there is the downside where you're not operating the burner at its highest efficiency. So what we're doing here is we have a fixed air setting, and we're using a modulating gas valve to control the gas flow to the burner. So at high fire, we're firing on ratio or possibly a little bit excess air. But when you go to low fire, you have your gas at your minimum, but your air is still at your high fire. Again, you're getting excellent mixing here, but your burner efficiency is very low. Cross-connected modulated ratio control. We see this this system quite often. This is your typical ratio control system. So what we do here is we modulate the air, and we use a ratio regulator in the gas line to follow the air. Now this works well to keep, in an attempt to keep the burner firing on ratio, keep the burner firing efficiently. The issues we have here is that when we come off of high fire, you're losing that stirring action of the high velocity burner. So you're losing convection as you start to go down to low fire. The other issue you have is the ratio regulator is set at high fire, and you set the burner at low fire, or you set your bypass at low fire, and where the regulator goes from that point is a good guess. They're designed to track as close to linear as possible, but ratio regulators do not track linearly. There is some droop. Pulse fire control. In its simplest, here we're showing high-low firing. So we have a control valve in the airline and a ratio regulator, same as modulated. But the air valve is high-low, and that's adjustable. So you set your high fire air and your low fire air. And then you use your regulator to set your high fire setting. You use your low fire bypass. And now when the burner is at high fire, it's on ratio. And when it's at the low fire position, it's on ratio. And so your burner is firing efficiently. And there is none of that, you're getting maximum mixing, and there's none of that in the middle where you're not sure where the burner is, what ratio the burner is at. Pulse firing controls thermal input by cycling the burners from high to low or high to off to meet the application's demand. An air solenoid valve at each burner with adjustable minimum and maximum settings replaces the typical modulating air valve, and low fire is set by a bypass or around the pulse regulator. So the general system, burner is ignited at low fire, and each time the solenoid is energized, the burner will go from low fire to high fire. And we're talking about the entrainment and the stirring action in the furnace, create the convection, keep even uniformity. Air piping in each burner is identical. Changing the pulsing sequence or moving burners from one zone to the other can be done electronically. There's a little bit more work when you put a pulse fire system together on a new application, but if you're unsure about the process, or you're trying to change things about your process, or you need flexibility in your zoning, pulse fire does it electronically. So burners are zoned electronically as opposed to hard plumbing, and that's a big advantage on pulse firing. Temperature uniformity is increased with pulse firing via the convection. We're firing these burners at high fire. They don't sit at low fire as a heating component. Heating is done at the high fire setting. So those high velocity burners, we're using them to their maximum efficiency and getting them to move the product's combustion throughout the furnace. Pulse fire control facilitates the highest level of convection and heat to the load. Efficiency improvements up over 30%. If you look at your typical furnace, it's usually operating anywhere between 70 and 30% output under normal load conditions as an entire system. So you will see when all the burners are firing on ratio, you will see that savings. Firing the burners at their highest exit velocity, again, you're mixing the furnace gases, so you get a nice, even, uniform temperature throughout the furnace. Pulse fire increases the uniformity. Again, through the entrainment of the gases. Pulse firing works very well on high velocity burners, again, to move the gases throughout the furnace. It also works well on flat flame burners. Again, as you pull burners back, you're losing the thermal efficiency of the burner, and you're losing the mixing. Now, on a flat flame burner, when you go high-low, you are creating maximum efficiency of that burner, whereas on a high-velocity burner, you're getting the stirring of the gases. The flat flame will ensure that you're getting maximum thermal coverage of the flame. Pulse firing in radiant tube burners and self-recuperative burners. This is another application where pulse firing really stands out. In radiant tube burners, it enhances temperature uniformity and extending the life of the tubes. A big issue that we have found with traditionally fired radiant tube burners is that the burner will sit at low fire or at a low position, let's say 30 to 50%, and you get uneven heating in the tube, and you create hot spots at the burner side of the tube, at the burner end. So you'll get premature failures on the tube, and your heat to load is somewhat sacrificed. When you fire those burners at high fire, you're getting the full thermal efficiency of the tube, and the other issue you have is on pulse fire, when you shut the air off, you're not, or go to low fire, you're not cooling the tube. You're creating a nice, even, uniform temperature in the tube. On self-recuperative burners, pulse fire is required method for the burner firing rate. The high off, you get excellent tube uniformity and maximum efficiency on the recuperator. Pulse firing reduces the requirements for excess air. Again, going back to the fuel-only control. We're using the excess air to mix the gases in the furnace to create uniformity, but we're reducing the efficiency of the burner, and we're basically adding load to the furnace. So all that air has to be heated up to the operating temperature, and you're sacrificing your burner efficiency and your furnace efficiency. Again, pulse fire, when the burner is pulsed on, you're getting maximum velocity. During the off or low modes, you're not allowing this excess air, this excess load into the furnace, so you're increasing the uniformity of your furnace. Pulse firing reduces the requirements for excess air. If you do need increased turn down, or you have an application where excess air is required, there is a method around that which creates a wider burner operating range. So you can actually extend the operating range of your burner with this system. We call it heat-cool pulse control. And with the heat-cool pulse control, you have your standard air solenoid valve for a pulse fire system, your standard pulse regulator. But what we also do is we incorporate a second impulse bleed valve and an impulse bleed regulator into that gas line. What that allows us to do is to reduce the gas going into the system. So at those excess low firing applications, we've taken furnaces down from 2600 degrees F all the way down to 180 degrees F. So we've successfully pulled these burners down well below any furnace that would, a modulating furnace that would operate high-low, or a modulated high to low. This is a typical diagram of how we would do this. Your heat demand is across the x-axis, and the pulse bleed output is on the y-axis. So as you, at your 0% output, we are bleeding off all the gas impulse pressure. So if we go back to this slide for a minute, if we have our first regulator, our first upstream regulator, if we are firing at high fire, our air valve will be wide open, And this gas regulator, our upstream gas regulator, will be in the high fire position also. But what we're also doing is we're bleeding off that impulse signal to the second regulator. So the second regulator is completely shut. So the only gas to the burner is going to be that low fire gas. And that provides us our low fire maximum air position that we see here, all the way at the top. And as we go up in heat demand, as our heat demand increases, we're going to reduce that impulse signal so that, or increase the impulse signal to that downstream regulator so that, let's go back to this for a second, so that downstream regulator will slowly increase the gas as the burner goes to high fire. So we'll slowly move back to ratio control to the point where at about 30% output, we're firing back on ratio. Our low fire position is stoichiometric. And then again, our pulse output would increase from 30 to 100% on ratio. Here we show the typical modulating system and pulse control system on the plumbing. So the top picture shows your modulated control. You zone your burners. You control a group of burners with a modulating motor, zone air butterfly valve. So you're modulating your air, your gas is following at the burner, presumably. And in a pulse system, down here you're showing that all your burners get the same air and all your burners get the same gas. So each burner is independent, and you can then zone those, divide those out as you see fit. You can still, the upper picture shows 3 zones. We can divide that lower picture into 3 zones, 6 zones, 8 zones, 1 zone. However you need your furnace to be designed or your application, it can be also changed on the fly depending on how you operate your pulse system. So here we look at time over number of burners. This is how pulse firing works. Either you can look at it as high or off. It's probably easier to look at this graph and say off. But at high, we have a 4-burner system, and at 25% heat demand, one of the 4 burners is on at one time, and the other 3 would be off. And it's a 6-second time delay. You can, that time is adjustable. And at 50% heat demand, you can see that the same number of 4 burners, now when instead of having 1 burner on, you're going to have 2 burners on. And you can see how the timing will shift. And it goes up from there. And it's, again, it's not any step of, it's infinite. Some of the critical components are the air valve, obviously. This is a high cycle air valve. We did a 6-second time overlap on that last slide, last 2 slides. So you need components designed to cycle your burners that quickly. So you need a regulator. You need, if you're going high off, you need a gas valve that's designed for that. And you need an air valve. And you also need flame safety that can take that high cycling rate. So Kromschroder has specifically designed air valves for that. These are high duty cycle air valves. They can be slow opening, slow closing, fast opening, slow closing, and fast opening, fast closing. The Kromschroder pulse regulator. This is specifically designed again for pulse fire applications. So as the burner goes from high to low or high to off, the diaphragm is designed, it's balanced, so it's not designed to, it is designed not to oscillate. So you won't get a bouncing signal if you pulse burners too quickly. The Kromschroder ratio regulator also has an internal bypass. So it is a fixed internal bypass. There's also an adjustable bypass. Depending on your system requirements, you may need to switch to an adjustable bypass. If you need multiple points of control or a complex control scenario, instead of going with a solenoid-actuated butterfly valve, you can go with the Kromschroder IC actuator. Again, this actuator is designed for pulse firing. It will pulse at 7 seconds. It won't go down as low as 6, but it will do 7 seconds, and it will take the high duty cycle. This will allow you to do extremely complex pulse fire applications. So you can fire your burner high, low, off with this, or you can do an ignition set point that would be maybe higher than your low fire position. You can also switch this motor between digital and analog control. The Kromschroder solenoid valves, again, are specifically designed for the pulse fire applications, the high duty cycle. Kromschroder solenoid valves have a minimum duty cycle of 10 million cycles. They have integrated flow control built in, and on the right side of the screen you will see a combination ratio regulator solenoid valve. The nice thing about the Kromschroder valves is they can also be installed in the vertical orientation, allowing you to minimize your piping footprint. Pulse firing can also, a lot of people base that on, think there's a PLC involved in that. It can be done via PLC. Hauck and Kromschroder both have PLC systems designed. We can work with you on that. There's also, Kromschroder has developed a rack-mounted pulse fire flame safety with an integrated MPT pulse sequence controller. So you buy a flame safety rack from us that would contain your flame safety cards and this MPT card, and that would be the only instrumentation you would need. It would take your current existing temperature controller, take your 4 to 20 output, and it would translate it to pulse fire the burners. It makes for a very simple, very quick retrofit. If you prefer local flame supervision, we have the Kromschroder BCU. Again, the flame relay is designed to take the high duty cycle. The BCUs have built-in outputs for the gas valves and the air valves. So you provided a go signal, and it will cycle the air and gas valves as needed. Some pulse fire applications. Picture on the left is using burners with the IC40 controlling a butterfly valve, and the picture on the left is a line with the air valves, the solenoid-operated air valves. Again, here we have a solenoid valve. The actuator, motorized actuator, on a pulse fire system. And again, these are installed multiple applications, preheated systems. You can use preheated air on the Kromschroder butterfly valves. And again, with self-recuperative burners. Here we have the BCUs controlling the air and gas valves, and they are firing those burners high off. This is a rotary furnace, rotary hearth furnace, with the BCUs, complete Kromschroder controls, and LBE burners, self-recuperative burners. Pulse firing furnace pressure. Pulse firing does make furnace pressure more difficult, but with proper equipment design, engineering, it's easy to overcome. So some of you may be concerned with pressure fluctuations within the furnace. As long as the flues are properly sized and you have proper pressure control equipment, there is little to no effect on your furnace pressure or furnace pressure design. As long as we stay ahead of the design, we can definitely design out any applications where tramp air might be coming into the furnace when the burner switched to low fire. Pulse firing advantages. We're going to save you fuel. Again, we're operating the burners at their most efficient settings and eliminating the need for excess air, or at least lowering it to its absolute minimum. We're creating convection within the furnace. So again, we're mixing the gases within the furnace, getting the heat to load faster, and thus reducing your runtime, the soak times possibly. improve the process, superior temperature uniformity. Again, we're firing these burners at high fires, so we're getting constant mixing within that furnace, getting all those hot gases to stir around. Lowering the NOx, again, firing the burners at their optimal setting, and the control versatility. If you find within your process, with pulse firing, if you find your process is not, you're not getting the uniformity you need, or zoning seems to be staggered, you can rezone and move burners, move the control scenarios so that you can improve uniformity or improve the mixing in certain areas, reduce capacity in certain areas, increase capacity in certain areas. Makes furnace design very, very flexible. Advanced burner control. Modern burner designs are enhanced by pulse firing. Then your high velocity burners, they're designed to mix those furnace gases at the high fire. So we're maximizing the benefits of modern high velocity burners. Ease of setup and operation. Again, if you're operating your furnace within between 70 and 30%, you might have somebody that tries to increase uniformity, or increase burner performance by detuning the burner to operate maximum at 70%. So again, you're going to make sacrifices somewhere where with the pulse fire system you have maximum flexibility of the burner. Again, you're only setting up high and low fire. Enable combustion systems to be compatible with modern computer controls and adaptable to future demands. So again, your electronic zone, so it's not, we're not tied to one actuator, we're not tied to one zone. As everything changes, you can get as complex as you want to be because each burner is its own, can be its own zone. Pulse firing. We did this visual representation, batch furnace via CFD model. Pulse fire control, furnace set point is 1800 degrees. We used 6 of the Hauck SVG 125 burners. We staggered the burner arrangement above the load. Load is 3 carbon steel rectangular ingots. Soaking stage of the heat cycle, so heat demand is 16%. Burner time on is 6 seconds. So, okay, so that is going to work. So as you can see here, the ingots are set up on piers, proper spacing, firing above the load. Again, the burners are staggered to fire between each other. And as you can see here, this is our computation of fluid dynamic modeling of firing the burners and how the gases are going to stir through the furnace. So as you can see, as the burners are firing, each one's mixing the furnace gases throughout the entire body. Again, for this representation, we just did a single plane, but if you were to switch it, you would see that the furnace gases would roll down the sides and swing back up through the back side of the burner. So we're mixing gases throughout the entire furnace chamber as the burners are firing. And this gives you a very good representation of what's going on, and you can only imagine what would happen if we staggered the burners high-low. In other words, mounted the burners on the left-hand side of the furnace underneath the load and go over. You get tremendous mixing of the furnace gases. This is showing you temperature uniformity throughout the heat as the burners are firing. The red on the burner will tell you which one is firing, just so you get an idea, and how the temperature throughout the furnace changes, and we're getting maximum heating to the load. Furnace load and temperature profile. So again, we're looking at the furnace and the furnace walls, fiber lined for maximum efficiency. And you can see the metal furnace, metal surface, and the metal center line. We have a nice rise time. We've applied this in many customers. This is a short list of some of our more well-known customers that are satisfied with, that have been turned on to the pulse firing methodology. and really seeing dramatic improvements in their furnace operation and possibly their, and in some cases, their furnace output. Here's a short video we did of a box furnace with furnace firing high-low. So you can see the burn on the low as it comes back down into low fire. And there's a burner in the back. You're kind of seeing a little bit of that. But that's essentially a brief overview of pulse firing and what we can do with it and how it would be applied